Hello, this will be a demonstration of Proposition 5 from Book 5 of Euclid's Elements, which says that if a magnitude be the same multiple of a magnitude that a part subtracted is of a part subtracted, then the remainder will be the same multiple of the remainder that the whole is of the whole. What this is going to look like is we are going to have two magnitudes, AB and CD, and from them we are going to have parts subtracted from them, AE and CF, and these parts subtracted are going to be, related to each other such that AB and AE are equal multiples of CD and CF. So the multiple that AB is of CD is the same multiple that AE is of CF. What we set out to prove is that the remainder of AB and AE will be EB, right? That EB is the same multiple of the remainder FD, right? The remainder of CD and CF is going to be FD. That EB is the same multiple of FD, that AB, the whole, is of the whole CD. We begin the bit of a strange step. We begin by making another magnitude CG such that the multiple that AE is of CF, EB will be that same multiple of CG. So AE and EB are going to be equal multiples of CF and GC respectively, which means then by 5(1), if we add these together, then AE is going to be the same multiple of CF, that AB, which is AE plus EB, is of, excuse me, I got these a little mixed up, of GF, right? GF is CG plus CF. Okay, cool. So AB is the same multiple as CF, that AB is of GF, but it was given to us that AE is the same multiple of CF, that AB is of CD, right? So AE and AB are equal multiples of CF and CD respectively. This was given to us. And so we can say, by a property of magnitudes, that AB must then be the same multiple of GF and CD at the same time. So AB is the same multiple of GF and CD at the same time, which can only mean that GF is equal to CD. Now, GF being equal to CD, if we then, excuse me, let me think just a moment. Let me think, I might have gotten things, I get things backed up? No, we're good. Okay, never mind. So GF being equal to CD, right, we had just established that. If we then subtract CF from both, right, we can say by common notion 3 that the remainders from equals being subtracted from equals are also going to be equal. So we can say that GC is equal to FD, right? So GF minus FC is GC, and CD minus CF is FD. So GC is equal to FD, again by common notion 3. But we had made AE and EB such that they are equal multiples of CF and GC respectively. That was our first step. So the multiple that AE is of CF is the same multiple that EB is of GC, which means that AE must be the same multiple of CF that EB is of FD, right? Because GC is equal to FD, so we can substitute GC for FD and we'll have the same expression. So AE is the same multiple of CF, that EB is of FD, but it was given to us that AE is the same multiple of AB, or AE is the same multiple of CF, that AB is of CD, which means then by a property of magnitudes we can collapse these statements and say that EB is the same multiple of FD, that AB is of CD. Now, this is what we set out to prove, which means we are done with the proposition, therefore, etc., Q, E, D. This proposition 5.5 is similar to proposition 5.1, right? The algebraic formulation of 5.1 involved the distributive property across addition. This one is across subtraction, actually. So if we consider CD, so if we consider like two magnitudes A and B, right, where CD is A and CF is B, what we're proving is that if we have equal multiples MA, and we subtract it from MB like that, we will get M minus AB, which means that M times A minus B is the same multiple of A minus B, is the same multiple of A minus B that MA is of A or that MB is of B. So yeah, this is like 5-1, where 5-1 had an addition sign here. 5-5 has subtraction. So both these propositions constitute the whole distributive property that we know. So that's quite cool, I think, at least. So I've got nothing else to say about this proposition, so I'm going to end the video here and move on to 5-6.